Alright, so what are convolutional neural networks? Convolutional neural networks are very similar to ordinary neural networks. They are made up of neurons that have learnable weights and biases. Each neuron receives some input, performs a dot product, and has an activation function. CNNs make the forward function more efficient to implement and vastly reduce the number of parameters in the network. In the image shown here, we can see on the left-hand side a regular three-layer neural network. On the right-hand side, we can see a convolutional neural network that arranges its neurons in three dimensions: width, height, and depth. Every layer of a connet transforms the 3D input volume to a 3D output volume of neuron activations. So let us take a look at the layers that make up the CNN. Firstly is the input layer, which will hold the raw pixel values of the image having the shape of width, height, and depth. Depth here is denoting whether the image will be an RGB image, then it will have a value of 3, or the image will be a grayscale image, then having a value of 1. The convolutional layer will compute the output of neurons that are connected to local regions in the input, each computing a dot product between their weights and a small region they are connected to in the input volume. Basically, the layer will employ number of filters of a specific kernel size to convolve with the same local region on the image to get features. The ReLU layer is an activation layer which will apply an element-wise activation function such as the max 0, x thresholding. Any negative value given to the activation function will be thresholded to 0 and the positive values will remain as is. The pooling layer will perform a downsampling operation along the spatial dimensions, width and height. Finally, the fully connected layer will compute the class scores or the regression values as in a regular neural network. So here we can see how a convolutional layer is working. We can see a convolutional kernel of size 3 × 3 being convolved with the same size in the image. This convolutional kernel will be convolved with each and every pixel of the image, and then it will be extracting the features for the next step. Here we can see how a pooling layer works. On the left hand side, the pooling layer is downsampling the volume by half in the dimensions of width and height. We can see that the original sample volume is 224 x 224 x 64, and the pooling layer reduces it to 112 x 112 x 64. Again, on the right hand side of the image, we see a single depth slice where a pooling layer of 2 × 2 filter is used. The original image has a 4 × 4 size, and after the pooling layer, it has been reduced to 2 × 2. So how will we be implementing our CNN and web app? We'll be implementing a CNN model using TensorFlow and the high-level API Keras. We can access the layers mentioned earlier from TensorFlow and set the hyperparameter ourselves. We will be making a deep CNN model for our project. After the deep CNN layer, finally we'll be having a dense or a fully connected layer dealing with classification and regression. We'll also have an input layer defining the size of the image being fed into the network. Lastly, after training, we'll save our model and make a Flask app for this project. Alright, now that we have loaded our images, we can proceed with creating the model. So firstly, we'll deal with gender prediction. Gender prediction, as we know, is a classification problem and has two classes, 0 and 1. 0 corresponding to the female class and 1 corresponding to the male class. So let us store all the images as a NumPy array in the variable x, and let us store all the targets as a NumPy array in the variable y. Now we're going to reshape x to let the model know that there are 10,702 samples, and each sample is of size 128 × 128 × 1. And then we reshape our target variable to show that there are 10,702 targets. Finally, we divide all the values in the NumPy array x by 255 to perform normalization of the images. This normalization will bring down the pixel values from the range of 0 to 255 to 0 to 1. Finally, we print the x.shape and y.shape. We can see here that there are 10,702 samples. Now we'll be creating the deep CNN model for our gender prediction. So let us import the sequential class. So we'll take an instance of the sequential class since our model needs to be a linear model. Then we'll import the model and load model class and function. Next, we're going to import the dense, global average pooling, conv2D, max pool 2D, activation, and batch normalization layers from keras.layers. So before creating the model, let us create a block which will have certain layers connected. This will help us to reduce the lines of code by just calling this function and creating multiple layers as blocks. So let us see what this block has. In this block C function, we are passing it the previous layer or previous block. We are passing the filter numbers and we are passing the kernel sizes. With that, we are creating a new convolutional layer connected to the previous block. The convolutional layer will have the filter number, the kernel size, and padding will be same. Connected to that will be a max pool layer of size 2 with strides 2. And connected to that will be a batch normalization layer. And then connected to that will be the activation layer, which has the value ReLU. Finally, we return that block. So let us define the model now. So let us make an instance of the sequential class, model gender, TensorFlow.Keras.Sequential. The input we'll define as an input layer using keras.layers.input. We know that the shape is 128 cross 128 cross 1. Now we define an initial convolutional layer attached to our input layer. This convolutional layer will use 4 filters, each of size 3 cross 3, and then it is further attached to a max pooling layer of size 2 cross 2. After this, we are sending this initial block to our block C function to create multiple blocks. We can see here, we are sending C0 block to block C to create the block C1. The block C1 will have 16 filters in the convolutional layer, each of size 3 cross 3. Similarly, C2 will have 32 convolutional filters, each of size 3 cross 3, and so on. Finally, we get till block 6 and we add a global average pooling layer to block 6. And to that, we add an output layer with one dense neuron with an activation of sigmoid. Once our entire network is created, we can configure the model to use the input as the input layer mentioned here and use the output as the last block that we mentioned here. Now that we have made the model, let us compile the model. Since it's a binary classification problem, the loss will be a binary cross entropy loss. Optimizer is Adam and the metrics will be accuracy. Let us take a look at the summary of this model. So we can see we have around 190,000 trainable parameters or weights. So let us fit this model using our X and Y data. The steps per epoch is open to experimentation. I use this particular value since it was giving me the best efficiency and accuracy. Validation split is kept to 0.2 so that 20% of the data here passed to this function is kept as validation. So I've already pre-trained this model for a larger number of epochs as shown here and then added 5 more epochs at last for training. Since it takes a lot of time to train, I'm not showing it here. So we can see here that we have got finally a training accuracy of 94.78% and a validation accuracy of 96.03%. Let us plot this. So we can see that there's a steady increase in the last 5 epochs of training in the accuracy and a steady decrease in the loss in the last 5 epochs of training. So finally, we can save this model as model gender.h5. Now, let us come to the age prediction model. Again, we'll be using the same X variable for our training. We'll just change the Y variable to get the age values as a NumPy array. Now, We are using the same model here as shown in the gender prediction model, but there are few changes to the fully connected layers. So we can see here, till this portion here, we are creating a deep CNN model with the C6 block being the last block and then a global average pooling layer being added to it. After that, since this is a regression problem, we'll have to flatten the 3D volume to a 1D feature dimension so that it can be input into the neural network for regression. After flattening, we take one dense layer with 100 neurons and keep the activation as linear. Then we add another dense layer with 50 neurons, keeping the activation linear. And finally, we have an output layer with one dense neuron, keeping the activation linear. Finally, we again create the model using Keras.model with inputs as the input layer and output as the final block here. After creating this model, let us compile it. This time, the loss will be mean squared error since we are dealing with regression problem. The optimizer will remain the same, Adam, and the metrics will be MSE. Let us take the summary of this model. Alright, so we can see that we have around 200,000 trainable parameters or trainable weights. Let us fit this model. So I have trained this model for more number of epochs than shown here, and I'm just showing the last 10 epoch training here. So we can see here that finally we have a steady decrease of the loss and we get around 87.798 MSE value. And in validation loss, we get around 76.67 validation loss. When we plot the history of the fitting, we can see that there is a decreasing trend in both the validation loss and training loss. Finally, we can save this model as model age.h5. So let us test this model. So we are using model gender.predict to create our predictions. Then we can see that comparing it to a slice from 5 to 15 range, we can see that these predictions are matching. Next, we'll be predicting using our model age in a similar way. And then if we print it and compare it to our actual values, we can see that they are somewhat similar. We can see there's not much of a difference in the age. Finally, let us print a confusion matrix to see the accuracy and precision scores. So we are using cbond to print our confusion matrix. We are using the confusion matrix function from sklearn, which we imported here. And then we are importing accuracy score, precision score, recall score, and F1 score. This kind of score is only possible for classification problems and not regression problems. So we can see here that in the confusion matrix, we are getting an F1 score of 0.9548. That means we are getting an F1 score of 95.5% and an accuracy of 96.11%. For our regression model, we can import the R2 score and check how our model has performed. So here we can see that we are getting around 80.14% accuracy.